last time we were together, we were discussing the concepts of acceleration, velocity, displacement versus distance. Okay, and we said that the displacements, the velocities, and accelerations are actually vectors. Each one of them is a vector because it has a direction. Okay, so when we talk about I am going at a certain velocity, I have to have two pieces of info. I have to have a magnitude and a direction. Magnitude, in this case, how fast, and direction, in which direction. Let's call it which way, shall we? That's very important because we need to know both pieces of information. And acceleration is the same. I could be accelerating upwards, which means I'm taking off like a rocket, right? I could be accelerating downwards, which means I'm in free fall. Okay? So it's very important to have both. Now, let's look at an example, shall we? Now, in Newton's laws of motion, as with physics generally, I tell my students, guys, draw it. Make a drawing. Become one with it. Understand it. Don't look at it dispassionately. If it's about an apple falling from a tree, look at the apple. Think what the apple's going to do. Half of this is actually a logic process, right? It really is. It's what's happening out there in life. If I apply the brakes, I am going to decelerate. I am going to stop. So let's just think logically, first of all. Let's look at the problem. A truck is at a red traffic light. Okay? The traffic light turns green. After 60 seconds, the truck is traveling at 120 kilometers per hour. What is the acceleration? Right. Now, let's just first of all draw it. The truck is at a traffic light, all right? There it is, okay? It is at a traffic light which is red, right? The traffic light then turns green. What does the truck do? It moves, right? So the truck moves that way, right? So my first situation is the truck starts to move. Then I say, right, they say 60 seconds later, it is traveling at 120 kilometers per hour. So let's draw from here to there. Delta t is equal to 60 seconds. The truck is now here, isn't it? And it now has a velocity equal to 120 kilometers per hour, right? So let's have a look. First of all, let's say, do we know how far? Do we know the delta x, which is the displacement, right? We're going to get to all these terms shortly. Okay, so no, we don't. What do we know? Do we know the velocity here? Yes, we do. It's at 0. Please note I wrote meters per second. Why? Because the truck was at a red traffic light. Please look out for things like that, and also a term called at rest. The moment we see at rest, it means 0 velocity. Okay? It has stopped, okay, before it's going to go, or it came to a halt after it was traveling, right? So now this one is, it was at 0, and then it went faster, and after 60 seconds it was that. Right, now what do? We say, okay, remember way back we had, going way back, let's have a look at velocity. Velocity is measured in meters per second. So it's actually delta x over delta t. Delta x is displacement. Delta t is equal to time. Okay? It's displacement over time. Right? Right. Now, we don't know what the displacement was because we don't know how far it went. Okay? Right. Now the next thing is acceleration. We define as delta V over delta T. Okay? Delta V is equal to change in velocity. Delta X is actually change in position. It's change in position, and over time, delta V and obviously delta T again is change in time. Right, so what do we know? Let's have a look. Delta V, do we know? Well, first of all, the first thing I haven't done is what do we do when we see things traveling at 120? We convert. To meters per second. How do we do it? Well, we go back to the table and we say, right, Kilimanjaro, kilometers, it's going to meters. It was hectometers, King Henry, decameters, Dida, miserable death, right? I am going 1, 2, 3 down. If I'm going down, okay, what am I doing? I am multiplying. So I say, right, therefore I've got kilometers per hour, and I want to change that to meters per second, right? So what do? Kilometers to meters, I must times by 1,000, and over here, hours to seconds times by 3,600, which then means I must times that by 1,000 divided by 3,600. Okay? 120 times 1,000 divide 3,600 is going to be equal to 33.33 meters per second. 33.33 meters per second. That is the velocity at this point, isn't it? That's what we are traveling at there. Now, please remember this, that in physics, in chemistry, generally when we see delta, it means change. Right? Change. Change means subtract one thing from another. And it is always going to be the final one minus the initial one. Okay? So in this case, what is the final velocity is 33.33 minus the initial velocity. Could be velocity, could be position, could be temperature. Okay? Change, you take the final initial. Energy states, which we'll be getting to in grade 11 and 12. Okay, a little bit here as well. Okay, is going to be, so delta V is going to be 33.33 meters per second. Okay, it is positive. Why? Because my velocity has increased. Technically, it's a positively sloped graph. Okay, so we've got that now. Okay, so therefore, can we work out acceleration? Well, acceleration is going to be change in velocity over change in time. Change in velocity is 33.33. Change in time, we said after a minute. Hang on. Let's go back and say, what did we have here? We said time was after 60 seconds, a minute, it's already been changed. Okay? So therefore, we have to say divided by 60, which is going to be equal to 33.33 divided by 60 is going to be 0. meters per second squared, and I'm just going to round it to 0.56 meters per second squared. All right? Now, all right. Let's have a look at the next part of this problem. They tell us, right, that the truck, okay, the truck is going to be traveling at this speed for 1.5 hours in a straight line east. Okay, so what do we do? We start off, we draw our truck again, and it's got a velocity here of 33.33. Okay, this is now, and it's going to travel for 1.5 hours. So delta t between the points A and B is equal to 1.5 hours. Okay, right? Now, the velocity over here is still 33.33 meters per second, right? Can you see there's no acceleration, because acceleration is delta v over delta t. Delta v would be 33.33 minus 33.33 over 1.5 hours, which we're going to convert now. Let's convert it. Time, first of all, 1.5 hours is going to be equal to 1 hour and 30 minutes, okay, which is going to be 60 plus 30 minutes, which is 90 minutes, which is equal to minutes to seconds times 60. So it's 90 times 60 is equal to 5,400 seconds. And then on our little diagram, we say, what do they want? Displacement. They want to know delta x, right? Well, let's have a look. Okay, that's over 5,400. I just forgot to put that there. All right. So now, let's see. We said, okay, what is the displacement, right? Well, velocity is equal to delta x over delta t, isn't it? Right? What's velocity? Velocity is 33.33. Okay, is equal to delta x over 5,400. Therefore, delta x must be equal to 33.33 times 5,400, which is equal to times 33.33, which is equal to 180,000 seconds, okay, or meters rather, and I'm going to call it, that's 180 meters, which is going to be equal to 180 kilometers. All right? That's how far it travels, okay? Now, the next step, okay? Now I'm at B, right? Now we're at B. We are at B, okay? We, in other words, are traveling along, okay, at our velocity equal to 33.33 meters per second, right? So we do our drawing. Then they say, the truck sees a railway crossing ahead. So over here, it sees a railway crossing, all right? Now, it starts to brake. It takes the truck 12 seconds to come to a halt, right? So it's my new situation. So what do I know? Velocity equals 0 meters per second here, and delta t equals 12 seconds, right? Okay, calculate the acceleration. Right, acceleration is delta v over delta t. Delta v is the final velocity. It's that one. The end velocity is 0 minus 33.33, okay, over 12 seconds. So we can work out the acceleration is minus 33.33, okay, and let's divide that by 12 seconds, which is coming to minus 2.78 meters per second squared. Minus means it's accelerating. The acceleration is that way, is this direction. In other words, it's acting against the movement, isn't it? It's slowing the truck down. Can you see that the logic here? It's actually quite logical. Ask yourself what's really happening. All right. Well, there we know the displacement. Okay. Well, we know the acceleration over there, etc. Now, how do we link How do we link all this lot together, right? Let's first of all just look at some of the terms we're going to come across. First of all, we're going to come across, well, let me introduce it. This is going to be Newton's laws of motion. Newton's laws of motion, okay? And let's have a look and we say, okay, in Newton's laws of motion, first of all, delta x is going to be change in position, which is change in displacement. All right? That's delta x, right? Let's have a look at Vf is final velocity. Okay? V initial is initial velocity. Right? Okay? And acceleration, delta t is equal to time. Okay? Change in time. Okay? And lastly, accelerate, A is acceleration. Okay, I am going to respell that. Acceleration. Right? So what are we saying here? We're saying that these are going to be standard terms. Okay? Now, you will see that you will get a set of equations, standard equations that are going to be given. I'm going to reproduce them here. Vf is equal to Vi plus A delta t. Vf squared equals Vi squared plus 2A delta x, right? Delta x equals Vi delta t plus a half A delta t squared. This is equation 1. And this is equation 2. And this is equation 3. Doesn't matter what order. And delta x is going to be equal to a half Vf plus Vi times delta t. Okay? That's equation 4. Right? Now, we are going to be looking at these. All right? These are Newton's laws of motion. The critical thing with any of these problems is to draw it, because I can assure you that the chances of an error, if it's not drawn, just multiply, because you're not exactly sure which one you're talking about. All right? And we're going to be going not with just one calc, we're going to be adding different stages on. So the first part is, in any problem, let us take the truck that we just had. It did what? It was at rest. Then it accelerated for a period of time. Okay? In other words, it sped up. Then it traveled at a constant velocity, right? Then it slowed down again. All right? It may have then turned around and come back to us, right? But if you break each and every mechanics problem down, that goes from this here, this part of it, and get into the habit now. This is the Newton's laws of motion. When we move on, we're going to be doing motion in two directions. We're going to be doing energy. We're going to be doing momentum. All of those we split into sections, and we analyze the section by itself. Okay? That's what we do. That's how we do these problems. It's how we solve them. So in this situation, right, we've got these here. So the first session, the first thing we do is let me just put my glasses on. How do we approach it? Step 1. Step 1, draw. Now when I say draw it, please, I know time is a constraint. You make it a little drawing. Now you don't have to draw a car, you just draw a box. Put wheels on it if you like, okay? And draw if it's going up a hill. Just draw what it's doing, because that's going to help us to solve it. The second thing is when you do your drawing, please be decisive about it. Give yourself space. Please don't draw a drawing like this because you can't see it, and neither can the examiner when they're marking it. They cannot see what you've done. The errors in there will be enormous, right? Make a positive drawing so that you can go back and put in the results. Remember what I said about electric circuits. When you finished with something, you go back to the circuit and put the answer in. Guess what? Wash, rinse, repeat. You do the same here. Physics is a pattern. You make a drawing of it, you put down what you know, you put down all that's given, then you look for the one that you've been asked to find. Find a formula and solve for it. The key being the drawing. Okay? Now, step 2. Step 2 is, big word, discretize. But I'm going to put in split up into different sections. How do you decide? Right? How do you decide where to split it up? You look for place where things change. Okay? In other words, change of velocity, change in time, change in acceleration. Okay? All of those things mean that you can't apply the formulas, you have to go back and reapply them because one of them has changed, right? So if one of them changes, okay, then we go back and we have to go and resolve for the lot again. Please remember that at rest means 0 velocity. All right? Then we're going to go and we're going to go back and have a look at our truck, okay, and we're going to do a few calcs on that when we come back, and we're going to look at this graphically, okay. So in the next section we're going to do an example or two of this, okay. We can just think of them, all right, that's not too serious. I'll do one with something dropping off a building or whatever the case might be, and I will go back to our truck and we'll look at various bits and pieces, okay. There was another thing I forgot, all right. Step 3, convert to meters, kilograms, and seconds. Always take those guys. Do the conversion, okay? When you put down your known figures, okay, I'm going to go through it, then you do your conversion, always, okay? That must become a rigorous part of your routine, is doing those conversions. Right, I'm going to just leave it at that, and then next we'll continue with the rest of these with some examples and stuff. Then we'll get on to graphs, and last of all will be ticker timers. So I'm guessing probably maybe 2 or 3 more sessions, and then we've handled all of your physics for grade 10. Thank you for watching, and I'll see you and we'll carry on in the next one.